A similar formula was also used by Russell, 2003, in order to estimate the errors involved in the comparisons with her models of spiral arms with the observed high regions. Since a simple model of circular velocity does not adequately reproduce some of the characteristics observed in the LV diagrams, it is also necessary to introduce perturbation terms in the calculated velocities. The use and the justification of these terms were first described by Ogorodnikov, 1958, and is explained in detail by Misharov and Zanina, 1999 AB, and Lepine et al. 2001. As explained above, the procedure consists of transforming xy galactocentric coordinates of the arms into velocities. So each point with an xy coordinate has a corresponding point, L, V, in the LV diagram that is calculated as explained below. The longitude is directly obtained from xy galactic coordinates, in which R0 is equal to 7.5 kpc, which corresponds to the distance from the Sun to the galactic center. This value is actually largely used, and one of the first mentions of its use was by Reed, 1993. The final velocity is given by in which things end in the air tangential velocities projected in the xy plane, and V1 is calculated from the expression below. VRR means the value of the rotation curve for a given galactocentric radius, R. The pro term corresponds to the perturbation in rotation and soon as the projected velocity of the Sun calculated by the relation, in which VOT equals 12.8 km per second. The term which describes the radial and angular perturbation components is given by the term A2 is described below, in which RQ is set equal to 8.3 kpc and represents the co-rotation radius, section 3.5. The term A1 equals minus 0.4 represents the phase variation. The amplitude of the perturbation in the rotation is described by the expression, in which A3 equals 12.5 a log r/rc. Due to the existence of the Lindblad internal resonance, ILAR, see Amaral and Lepine, 1997, AL97, the terms A2 and A3 are set equal to 0 for R80 degrees. This arm is a prolongation of arm 4 with I equals 11.55. The continuation of arm 9 is arm 16, heavy blue line, with I equals 9.0. McClure-Griffiths et al. 2004, while analyzing ACTA data, detected a structure that extends from L equals 260 degrees to 330 degrees that they attributed to a spiral arm with I equals 9.0 degrees. This structure was also found in our results as represented by arm 12 with I equals 11.5 degrees. Kerr, 1969, published latitude velocity diagrams in which a bridge appears in the third quadrant toward positive velocities. Kerr, 1969, also presented maps with this feature extending from L equals minus 150 degrees to minus 70 degrees. Davis, 1972, also interpreted this region as relating to the end of a spiral arm associated with high-velocity clouds. Since the first high observations, the existence of a hole was seen in its distribution in the galaxy, Kerr 1969 and Burton and Gordon 1978. In these works, the authors noted a gas deficiency in the radial gas distribution for R equals 11 kpc, assuming 0 South African rand equals 10 kpc. From the theoretical point of view, Moropik et al. 1972, Kreis and Menasier, 1973, and AL97 also found evidence that the co-rotation point, i.e., the point where the rotation velocity of the spiral pattern coincides with the rotation curve of the gas and stars, could be located in the solar neighborhood. The effect of the co-rotation can be understood in the following terms: there is a region where movement exists pumping the gas inside and outside, resulting in a deficiency of the gas in these regions. This effect was also studied in detail by Suchkov, 1978, Goldreich and Tremaine, 1978, Gorkovyi and Friedman, 1994. Misharov and Zanina, 1999a, also found evidence that the co-rotation point would be located near the solar radius. Amoris, Lepine and Misharov, 2009, ALM09, analyzed the high spectra of the whole galactic longitudes range in steps of half a degree, with galactic latitudes in steps of 1 degree in the range plus or minus 5 degrees, plus the additional latitudes plus or minus 10 degrees, detecting for each spectrum the velocity of the deep minima which are present, simply by identifying the channel with the lowest value of antenna temperature. They obtained that distribution of the density minima in the galactic plane, derived from their kinematic distances from the Sun, is shown in. The minima observed at different latitudes are all projected on the galactic plane. The ring-shaped gap is circular and very clear. It looks like the Cassini division in Saturn's rings. Galactocentric distance distribution of the gaps for the whole sample of measurements including different latitudes. The Gaussian fit is centered at 8.25 kpc, adapted from ALM 09, figure 4. The analysis of high spectra allows to determine the points in which the high has a gap in its distribution by means of an empirical method. The histogram with the galactocentric radius of each one of these gaps showed that the most of them are located nearest the solar radius, which highlights the fact that the Sun is located at the co-rotation point in the galaxy.